Hey guys, welcome back. So in this video, based on the request that is made in the Q&A section, I'm gonna explain an algorithm called as Dijkstra's algorithm. Okay, Dijkstra's algorithm. Dijkstra's algorithm or Dijkstra's algorithm. It doesn't matter whatever the way you pronounce. It matters what does it exactly do. Okay, so Dijkstra's algorithm solves a problem in graphs data structure. Okay, your linear search or binary search, which solves the problem of searching an element in the array data structure, right? You know that an algorithm always exists to solve a particular problem, right? To provide an optimized solution to a problem, right? That exists in the data structures, right? So there is a problem which exists in the graph data structure, and that will be solved by this Dijkstra's algorithm, or that will for that problem Dijkstra's algorithm will provide an optimized solution, right? And specifically we're going to apply this Dijkstra's algorithm only to one particular type of graph. That is, graphs have a basic type of classification called as weighted and unweighted, right? Weighted and unweighted, and we're going to apply this Dijkstra's algorithm to only weighted graphs. Okay, and you will understand why at the end of this session. Okay, we are going to apply Dijkstra's algorithm only to the weighted graphs, and the graphs may be directed or undirected, but I'm going to take a undirected graph. Okay, so remember, this algorithm is applied for weighted graphs. Okay, and so what is the problem exactly? Okay, what is the problem? The problem is finding the shortest path. Okay, shortest path from the start vertex or starting vertex to any other vertex in the graph, to any other vertex in the given graph. So let me explain the problem first. After that, I'll tell you how the Dijkstra's algorithm solves that particular problem. This particular problem, Dijkstra's or Dijkstra's algorithm, right? Okay. Before that, let me tell you the meaning of each and every word in this problem, right? There is a term called as start vertex. What do I mean by that? Do I have any start vertex for a graph? Please recall, for a tree we have a starting node, right? That is called as a root node. Okay, say for example, this is a binary tree. Let's assume that this is a binary tree. Then I'll start traversing the tree only from A, right? Because this is the root node. Okay, there is something called as root node for a tree. But for a graph, do I have any root node or do I have any starting vertex? No, right? For a graph, I do not have any starting vertex. Okay, but I have to assume one in order to solve this Dijkstra's algorithm, right? You can assume any node as your starting vertex. Okay, any vertex as your starting vertex. For example, this is a graph. Okay, this is a simple graph. Okay, and you can assume either A as your starting vertex or B as your starting vertex or C or D. Okay, so you have to take a starting vertex, guys. Okay, and from that starting vertex, say for example, I am assuming A as my starting vertex. From that starting vertex, what is the minimum distance to achieve each and every node? Okay, to visit each and every vertex, not nodes, I'm sorry, vertex, right? Okay, let me give some intuition on that, right? Let me take a weighted graph. Okay, let me take a weighted graph. Okay, so this is a weighted graph, right? Let me assume the distances to be 1 2 3 1 4, right? So these are some distances. Okay, so assume these weights are distances between the respective nodes. Okay, 4, maybe you can assume any units. Okay, maybe 4 kilometer is the distance between C and D, but exactly they are units. Okay, so they are called as weights. All right, now I'll assume A to be my starting vertex. So A as my starting vertex. A as my starting vertex. So from A, I have to find the shortest distance to any other node or any other vertex, right? From A, I have to find the shortest path, okay, shortest path to any other vertex in the given graph, right? Okay. So what do you mean by shortest path, by the way? Shortest path is, let me assume that from A to B, I can go this way. I can take this way to go from A to B, and this cost me a weight of 1 unit, right? Only 1 unit distance between A to B. I can also go from A, C and D, right? And this cost me a distance of first moving 1 unit, then moving 3 units. So 4 units, right? That is one path from A to B. Okay, that's not a direct path. Okay, indirect path only, but the distance is 4 units. Now you tell me which, and there is one more path also. There are a lot of paths through which we can move from A to B, but let me assume two paths. A to B directly, that is 1 unit. Okay, and AC to B, that is 4 units. 1 plus 3, 4 units, right? Now can you tell me which is the shortest path? Shortest path is moving directly from A to B, right? That is the shortest path because that consumes only 1 unit, right? So that has to be found, okay? Practically we can easily find that, okay? But that has to be found using an procedure, okay? Using an algorithm, and that algorithm is called as Dijkstra's algorithm, right? And Dijkstra's algorithm provides a procedure to find the shortest path from the start vertex to any other vertex. Okay, I hope it is clear. Let me take a very simple example and explain the working of Dijkstra's algorithm. Then I'll move to a complicated graph and apply the algorithm there. Okay. So first of all, let me take example 1 to be very simple. Very simple graph. Okay. It's gonna be this. Okay. A straight graph. Okay. So which has 4 vertices which are attached like this. Okay. Now in this graph, let me assume some weights. Okay, let me assume that this is 2, 1 and 3, right? So these are the distances or weights between the corresponding nodes. Okay, and let me take, first of all, you have to make 3 assumptions or 3 conditions for Dijkstra's algorithm, okay, or Dijkstra's algorithm, right? The first condition is take a starting vertex. Okay, that we know, right? We have to take a starting vertex. Okay, only one source. Okay, this is also called as a source, so only one source should be there. Okay, only one source should be there. Second one is find the directly connected nodes. Okay, find the, not finally, find the directly connected nodes, directly connected nodes or vertices. Let me go for the term vertices. Okay, find the directly connected vertices. Third one, assume all other vertices are at infinity. Okay, let me explain this shortly. Okay, so there are 3 main conditions. Please remember this 3 main conditions. This will highly help you to solve any problem using Dijkstra's algorithm. That means this problem using Dijkstra's algorithm, right? Okay. Now let me assume A to be my starting vertex. Okay. Anyway, I'm going to assume A only. So let me assume A to be my starting vertex, and let me denote it by some symbol, right? This is just for our understanding. It need not be done. Okay, just for my understanding, I'll denote this by a asterisk, right? Okay, so that's gonna be my starting vertex, right? Okay, now I'll put a tabular column here. The table should show what is the shortest distance between A to B and A to C and A to D, right? Okay, so I have to find the shortest distance from A to B and A to C, then A to D. Okay, only from the starting vertex I have to find the shortest path to any other vertices in the graph. Okay, any other vertices in the graph. I hope this is clear. So let me say the two vertexes. If I find from A to D, then D is gonna be my two vertex. Okay, okay, to where I am finding, that is two vertex, and the shortest and the distance or distance, yeah, distance is the second column. Okay, distance. All right, so I am currently in A, so my starting vertex is A. Okay, starting vertex is A. Okay, this start is not gonna change. Okay, starting vertex is not gonna change, but there is one more term called as current vertex. Okay, current vertex, and that will be changed often. Let me tell you how that will be changed often. Current vertex is different from the starting vertex. Okay, current vertex is different from the starting vertex. Okay, let me give a quick intuition on this current vertex. Okay, let me say A is my starting vertex, B and C and D are lot of vertices, right, that are connected. Okay, but A is my starting vertex. Now I may stand at B, then I can calculate the distance from A to D. Okay, then B becomes my current vertex. Okay, then I can walk to C, then I can calculate the distance from A to D. Now, A to D, now C becomes my current vertex, right? So, current vertex is the term which will be changed often, okay? The current vertex changes from one vertex to another. So, the idea is you have to walk through all the vertices and you have to calculate the distance from A to that vertex, okay? A to that vertex, right? Say for example, I can stand at B and I can calculate the distance from A to C. Okay, so anyway you are calculating the distance from A only to any other vertex, but the current vertex you can stand at any vertex. Okay, you can be at any other vertex. Okay, and calculate the distance. That is the meaning of current vertex. Okay, I hope it is clear. So now currently I am in A only. When I am starting, initially when I am starting, I am in A only, right? Let me name it as current. Okay, there is one more column called current. Okay, so I am in A only. Okay, I'll name it current vertex. I am in A only. Super, right? Now let me say I am. What is the directly connected node? Okay, the second step is find the directly connected nodes. Okay, directly connected vertices. Nodes and vertices, they are same. Okay, directly connected vertices. From A only B is directly connected. C is not directly connected. Okay, C has B inside it. So B in front of it. So C is not directly connected to A. Only B is directly connected to A. Okay, only B is directly connected to A. So what I'll do here is I'll write the two vertex to be B and I'll make a distance to be 2 because that is the distance between A to B. Okay, that is the distance between A to B. Only understand that only B is directly connected and the distance between A to B is 2. So I am writing 2 here, right, in the tabular column, right? Now assume all the other vertices are at infinity. Okay, this infinity denotes that those are not at all directly connected to the graph. Okay, that's it. All right, so I'll make it to be infinity. Okay, because let me assume I don't know the distance from A, so I'm assuming the distance is very high. Okay, so from C to C it is infinity and to D it is infinity. Okay, you can simply add and say the distance, but I'm explaining the workflow of the algorithm. Okay, that's why I'm taking it to be infinity initially. Okay, so understand that you have to make a starting vertex, that is A, and find the directly connected nodes, that is only B is directly connected. If I have one more node like this, then I can say E is also directly connected, but here unfortunately only B is directly connected. So if it is directly connected, write the distance. Okay, so 2 is directly written, and all the other nodes make it infinity. Okay, distance is infinity. Don't simply add and write, you make it infinity, right? Because let us assume that we don't know the distance, right? All right, now uh, now the current vertex is A and that is perfectly done. Okay, current vertex, we have written the distance. Now move to the next vertex. Okay, now I am moving to B. Now B is my current vertex. Understand, starting vertex is A only, B is my current vertex. Okay, so from I am at B now, and I'll be calculating the distance from A to C and A to D. That's it. Okay, A to C and A to D. That's it. Okay, but the current vertex should keep on changing. Okay, so now I am at B now. Okay, now I am at B. All right, now I am at B. Understand, from B what are the vertices that is directly connected? So only C is connected. Okay, only C is connected, right? So from C, only C is connected. So we are going to manipulate only the C value, because to B only C is directly connected. All the others must be infinity only. So I am going to manipulate the value of C. How I am manipulating? Let's check this method. Okay. All right. So you are at B now. You are at B. Now calculate the distance from A to C. Okay. This is 2 and this is 1. So 2 plus 1 becomes 3. Okay. This is 2 and this is 1. So 2 plus 1 becomes 3. So now you are at B. Distance from A to C is 3. You are calculating 3. Right. So whether 3 is less than infinity? Of course, right. 3 is actually less than infinity. So replace the value. See here, replace the infinity with 3 now. Okay, replace the infinity with 3. Understand that you have to find the shortest distance only. So if the distance is actually greater, if the previous distance that is noted here is greater than the current distance, then replace that value with the current distance. Sorry, replace that value with the current distance. Okay, initially I had infinity here. Now I find the path to be 3, the distance to be 3 from B. Okay, from B, I am standing at B and I am finding from A to C, that is 3. Okay, now initially I had infinity, but 3 is found to be lesser than infinity. So I am what I am doing here is I am replacing the distance with 3. Very simple, right? That's it. Okay, now is there any other connected nodes? No. So move to the next connected node. Okay, next current node. Okay, next node. Now C is gonna be my current node. Okay, C is gonna be my current node. Okay. Now you may ask a question. If I have two nodes like this, okay, two nodes like this, right? Let me say this is 3. Okay, the distance. So two nodes like this. I am currently standing at B and I have made all the changes in the distance. Now where should I go? Should I go to C or should I go to E? That may be a question. You should go only to C, because E has a distance of 3. C is the shortest path that is connected, which has only 1. So move to the shortest node, shortest vertices. So move to C only, right? Move to C only. Okay. Now you may ask another question. If I make this to be 3 and if I make this distance to be 1, now where should I move? You should move to E. E should be the current node. Okay, E should be the current node, because C has a distance of 3 and E has a distance of 1. So move to E. Okay. I'm explaining the scenarios, but anyway, in the example that we took, no scenarios like this, only one. So move to the current node, that is C. Okay, only one node is connected, so move to that node, that is C. So now I am at C. Okay, now I am at C. From C, which is the node that is directly connected, D is directly connected. Okay, D is directly connected. Okay, don't take B, because for B we have already written the shortest distance from A, so don't take B. Okay, you take D only. Okay, D is directly connected. So directly connected means, okay, then you calculate the distance from A to D. So 2 plus 1 is 3, 3 plus 3 is 6. Okay, 2 plus 1 is 3, total distance is 6. Okay, from A to D, right? Total distance is 6. So whether 6 is less than infinity? Of course, right? 6 is actually less than infinity. Now update. Okay, update. Only if it is the previous value is greater than the current value, you update. If the previous value is 10 and your current value is 15, then don't update it, because previous value itself is the shortest path, right? Okay, I hope it is clear. So after now I can move to D. Okay, now D becomes my current node, but from D I couldn't go anywhere because there is no connected node. So this should be the answer. Okay, so you can see from A to B the shortest distance is 2. From A to C the shortest distance is 2 plus 1, that is 3. From A to D the shortest distance is 2 plus 1 plus 3, that is 6. Okay, so we can easily find out like this. This is a very simple graph, so that it becomes very easy for us. I think you understood the procedure now. Now let me take a big graph. Okay, a larger one. Okay, so carefully watch this example that I'm going to give, because this is going to be very important, right? I'll take this to be A, I'll take this to be B, and I'll take this to be C, and I'll take this to be D, and I'll take this to be E. And if you have not understood this example, please watch this again and come back to the example number 2. Okay, please watch this with a keen observation so that you will be able to understand this. So this is the graph I am taking, right, with a lot of paths. Okay, so that is a challenge for me to find the shortest path, right? Let me take the weights. Let me take this to be 1, this to be 2, this to be 5, this to be 2, this to be 5. Let me take this to be 5, let me take this to be 2, right? So these are the weights that I am gonna give. Okay, now let me draw the table that we have drawn here, 2 vertex and the distance. Okay, okay, so first one is the starting vertex. Anyway, that's gonna be only one vertex, right? So let me not write it in a table, right? I'll give the current vertex, I'll give the 2 vertex. Okay, from A to, I'll be calculating a distance to a vertex, right? Some x vertex, and that is the 2 vertex. You know that. Then distance, okay, in units, right? Okay. Initially, not initially, the starting vertex is always assumed to be A, right? So let me assume the starting vertex to be A, and this is gonna be constant till the end of the algorithm, right? So let me indicate it with the hashtag. So the starting vertex is gonna be A. Initially, the current vertex is gonna be A. Okay, the current vertex is also A. All right, the current vertex is also gonna be A, but that's not necessary, right? Let me take it B. Okay, B to be the current vertex. Okay, anyway, starting vertex is A, and I'll take B to be the current vertex. So if I am at B now. I am at B now, so I have to calculate distance from A to uh, any other nodes. Okay, first of all, let me take the 2 vertex also to be B, okay, because now I have to write the distance from A to B, right? A to B, right? So A to B distance is what? 1. That is the shortest distance, right? Then I'll say 2 vertices C, D and E. I'll write all the possible vertices in the graph, guys. B, C, D and E. Okay, because initially I have to write everything. Okay, I have to write everything. Then you can see the current vertex is B. Okay, from B, which is the vertex that is directly connected? C and D, right? C and D are the vertices that is directly connected. Okay, C and D are the vertices that are directly connected. So you write the distance from A to C, right? This is 1 unit and this is 2 unit. So 1 plus 2 is 3. So that is the distance from A to C. You should go only this way because your current vertex is B. Okay, so you should go only this way. So from A to C, 1 unit plus 2 units, so 3 units must be given. Okay, if you are at current vertex B, then from A to C, then you have to move 3 units, right? So I am giving 3. All right, now I am still at the current vertex only. I'll calculate the distance from A to D. So again 1 plus 2, which is gonna be 3. Okay, which is gonna be 3 only. All right. Whether E is directly connected? No, right? E is not at all connected to B directly. Okay, there are 2 nodes in between. So let me make it infinity. Right? Let me make it infinity. Right? All right. Now my current vertex. This is done. Now I'll move to D. Okay, so now I'll move to D. Move to D or C. Okay, both are having the same distance, so you can move to either C or D. Okay, so let me move to D. Okay, let me move to D. Let me move to D. So my current vertex is now D. Okay, D. From D, what are all the nodes that are directly connected? C and E are directly connected, or B is also directly connected. But for B, the shortest distance is possible is 1. So I am ignoring B. I have already written the shortest distance from A, that is 1. It's not gonna change because there is only, it is directly connected. So I am ignoring that. From D, I can move to E and C because those two are directly connected. So I am going to manipulate the values of C and E in this table. Okay, should I manipulate the value of B? Because no need. Okay, so let me manipulate the value of C and E, right? C and E. So C is there and E is here. From A you should move to C, right? From A you should move to C. through the current vertex, that is D. So 1 plus 2 3 plus 2 5. So the distance is found to be 5, right? So whether 5 is less than 3, no, 5 is not less than 3, so ignore it, don't change, don't update anything. Okay, all right, so already we have the shortest distance, so let it be. And from D you start analyzing E. Okay, so I can move like this from A to D and to E, right? So 1 plus 2, okay, so 3 plus 5, that is 8. Okay, whether 8 is less than infinity, of course, right? 8 is actually less than infinity, so that should be put 8 here, right? I should put 8 here. Okay, all right. Now so I have manipulated the values of C and E. Okay, now let me move to the next node. Okay, from D I can either move to E or C, but E is shortest, E is 2, whereas C is 2, whereas E is 5, so I will move to C. Okay, I'll make C to be my current node. Okay, so C is now my current node, right? And from C, what are the values that I manipulate? I can manipulate either D or E. B need not be manipulated. I told you this is the shortest distance, so need not be manipulated. So I can manipulate the values of either C or D or E, because those two are directly connected, D or E. Okay, so I'm going to manipulate the values of D and E. Okay, how? From A, that is the starting vertex, through C you move to D. Through C you move to D. What is the distance? The distance is 5 plus 2, and that is gonna be 7. Okay, 5 plus 2, that is gonna be 7. So from so 7, whether 7 is less than 3, no, right? The previous value is 3, 7 is not less than 3, so let me ignore it. Okay, let me not update it, let me not update it, right? And I have to move to E now. Okay, so from A I have to go to E through C, because C is my current node. Okay, through C I have to move. So 5 plus 5 is 10, whether 10 is less than 8, no, right? 10 is not less than 8, so let me ignore this also, let me ignore this. Okay, so let me not update it, right? Let me not update it. From C, directly connected nodes are B, D, E, and A. A should not be going to A again. Okay, need not be going to B, because we have already visited B. You can see that here we have already visited B. B has already become current vertex once. So you should not move to D also, because D is already visited. You can move to E. Okay, even if you move to E, there are need not be some vertexes, some nodes are not directly connected, so you need not change any value. Okay, after the end of this particular algorithm, this is gonna be the distance, the particular distances that we are getting. Okay, all right, I hope this is clear. Thanks a lot.